Good morning. We're going to do 4.4 transformation of linear functions. So as you look at these functions, if you see this x plus 11 here, when we add a number after the function, it makes that function go up 11 units. So all you have to do is take your vertex, and I'm saying there technically is not a vertex, but the middle of the graph right here at 0, 0, and we move that up 11 units. So I'm going to do that here. And then our slope, you'll notice this slope goes up 3 to the right 3. And if we think about 3 over 3 and reduce that fraction, it becomes 1 over 1. So our m value is 1 over 1. Our b value, new b value here, is 11. So if we write our new equation in slope-intercept form, it's going to be g of x, which means the same thing as y equals x plus 11. And that slope would be 1 over 1. So all we have to do is count up the equivalent of 3 squares and write 3 squares. And then you'll notice here we ran out of room on the graph. So we can also go down 3 squares and to the left 3 squares. And then you can draw your line. Okay, looking at example number 2 here, if we subtract 8 from the x function, it's just going to take that graph and move it down 8 units. So we just move the middle of the graph down 8 units. And you'll notice here our slope is still 1 over 1. So we just go up 1 square, right 1 square. And then you want at least 3 points. You can have more, but at least 3 points to graph the function. And then make sure you have arrows on the end. The arrows on the end indicate that, and I forgot to put arrows on the first one. The arrows on the end indicate that the function goes on forever, both up and down and left to right, which makes our domain be all real numbers on both domain, all real numbers, and range, all real numbers. Now, because we have parentheses here, if we have a function where we subtract 7 within the parentheses, the function actually moves to the right 7 units. So from the center of the graph, I'm going to move that function right 7 units. I'm going to count up 1 square and to the right 1 square. I'm going to count down 1 square and to the left 1 square. And we'll write a rule for these two cases coming up here in a second. Okay, again, the domain for all of these linear equations is up 1 unit. The domain and range is always all real numbers. The slope is up 1 unit, right 1 unit, because we have no number in front of the x. I'm going to add a page here so we can write our rules down. So if we have a function, it's y equals, it could be f of x, g of x, h of x, the letter does not matter. Just generic y equals mx plus b form. Remember, that's called slope-intercept form. Where m is the slope and b is the y-intercept. So m is the slope, b is the y-intercept. Okay, so if we have y equals mx plus a number, that moves the graph up, whatever that number is. If we have y equals mx minus a number, then that moves the graph down, whatever that number is. Then if they give us y equals not absolute value, but the quantity, parentheses, x minus a number, the graph moves to the right, whatever that number is. If we have y equals, in parentheses, x plus a number, then it moves left, whatever that number is. Okay? So we have up, down, left, and right. So the parentheses are meaningful. However, when we do these graphs with the parentheses, they end up looking exactly like this one, which is confusing. But as long as you just pay attention to these rules over here, then you'll understand how the graph's going to move given whatever the conditions are. We're going to add to this list a few more because we have vertical and horizontal stretch and compression. We also have horizontal and horizontal stretch and compression. Okay, so moving up here, we're going to focus on number 5, and then we'll also do number 6. So as I look at this parenthesis here, and I think about our rule right here, if it's plus within the parenthesis, that makes it move left. So this function is going to move left 10. I'm going to write it to the right of number 5. And then the minus 1 at the end of the function, if I look at my rules, if I put minus at the end, that makes it move down, whatever that number is. So this function is going to move down 1 and left 10. So we take the center of our graph and we're going to move it left 10 units, which is all the way here at the end of the graph, and down 1 unit. Remember, our slope did not change. It's still on each one of these problems, 1 over 1. So we start with our graph left 10 units and down 1 unit. Remember, this graph is going by 2's, so we have to go in the middle of this. And then when we count up our slope, we just count up and we go up 1 unit, to the right 1 unit, and make a dot. And we can keep going on the dots, but you need at least 3 so that we understand you know what the graph is doing. Okay, and that's our graph. So we look at number 6 here. We see there's a minus within the parenthesis, so we come down here and look at our rules. A minus within the parentheses makes it go right, whatever that number is. If we have a plus after, then we look at our rule. Here's a plus after, and it's going to go up, whatever that number is. So we're going to write the rule over here. So it's going to move it right 9 units. And it's going to move it up 5 units. So as we count this out, we've got 8 over here. The graph goes by 2's, so that would be 10 at the end. So we're going to have it right in the middle here. But then we're also going to count it up 5. Again, it's going by 2's, so 2, 4, 5, right in the middle of that square. And we can make a dot right in the middle of that square. Remember, our slope is still 1 over 1. If I go up 1 unit and right 1 unit, I'm off the graph. So instead, I'm going to count down 1 unit and left 1 unit. If I go a negative direction both times, it's a negative over a negative, which is a positive. So we're going to go down 1 unit and to the right 1 unit. So I'm going to have my dots in the middle of all these squares, right? I could keep going with the dots if I want, but you don't have to. We'll do this graph in good old hot pink. All right, I'm going to move my line just up a little bit so I hit my dots a little bit better. Okay, and that's the new graph. So as we look at some of these story problems, they can be a little bit confusing. So let's go through and read the story problem. We're talking about bowling here. So the cost for Nobu to go bowling is $4 per game. The key here is that per. Whenever I see per or each, I always need a variable. Okay, and then we have plus an additional flat fee of $3.50. So that plus $3.50 is going to be the y-intercept of this graph. And if we look at the function, the cost can be modeled by the function f of x equals 4x plus 3.5. So we see $4 per game. We know we need a variable there. They're using x for that variable. The $3.50 is the additional cost for renting the bowling shoes. So that's why it's plus $3.50 right there. So they want us to describe this graph as it relates to if Nobu does not rent the bowling shoes. So if we do not rent the bowling shoes, what happens is this part of the function goes away. So if we look at this, the function with the bowling shoes looks like this. But they want to say how the graph changes if we don't have the bowling shoes. So our new f of x function is just going to be 4x. So what's the difference here? There's no 3.5 and there's a plus 3.5. Remember our rule, if it's plus after, it's going to move up whatever that number is. Okay, so the answer they're looking for here, so describe the graph of g of x. I should change that to g of x. Let me do that. Because once the function changes, you should have another different letter right here, right? Because these are two different functions. This one has plus 3.5. This one here does not. So they're saying describe the graph of g of x as it relates to f of x if Nobu does not rent the bowling shoes. So this graph here, this equation here would go up 3.5 units. That's all you have to say. So if we look at our next problem, Natalie has $2.50 in her savings account in which she deposits $10 of allowance each week. So we look for that word, each or per, and we know we have to have a variable here, right? So where W represents the number of weeks, and we're going to write a function g of W to represent the balance of Natalie's saving account if she withdraws $40. So this $40 is going to be subtracted from $2.50. So we're going to write a new function, g of W equals, I'm going to write the slope first here because I want to train your eye to always do that. So we have 10W, and then if I subtract the $40 right here from the $2.50, I have $210 left. So our original f of W function was 10W plus 250. And you'll notice a change here. This 250 got subtracted to 210 because she withdrew $40. So what's the translation of f of W that results in g of W? So that would mean this 250 went down by 40. So we would say down 40 units. In this case, down $40. Okay. So just quickly talk about the next story problem because we don't need to keep going on this. So originally, we're talking about renting a paddle boat. The cost is $8 per hour. That's why we have a variable next to the 8. And we have a non-refundable deposit of $10. If that increases to 15, this number here just increases to 15. and that graph would move up 5 units. Okay. All right, so we're going to continue with our rules here. If we multiply the function by 5, we're going to write a new rule here. So if we have y equals some number in front of the function, what that is a vertical stretch by 5. The y values will be multiplied by 5, which makes the graph much steeper, right? If we had a regular old coordinate plane and our y equals x function looks like that, then this graph is going to be way steeper because the y values as we go up here are being multiplied by 5 units, which makes it go up much faster. Actually, I wanted to write an x right here, not a 5. Okay, so vertical stretch by whatever that number is. I wrote the 5 over here as well. By whatever that number is, which again makes the y values go up 5 times as fast. So if we have this function right here, notice the difference. We have a whole number here, and over here we have a fraction. So for number 10, the units are going up 5 times as fast. For number 11, they're going up 1/3 as fast. So if we have a fraction here, so y equals, say it's 1 over some number times x, then it's going to be a vertical compression. The graph is kind of getting smushed from the top. By 1 over whatever that number is. Okay, so if we look at this graph here, instead of going up 1 unit to the right 1 unit, we're going to go up 5 units to the right 1 unit, and then up 5 units again to the right 1 unit. So that graph's going to go up way steeper. So as we count this out, we go 2, 4, 5, right 1 unit. Remember, it's going by 2s, this graph, and then we can count up 2, 4, 5, right 1 unit. And then you can see how much faster that goes up. Remember here, y equals mx plus b form, our y-intercept is going to be 0. And then we can draw the line. So much, much steeper. Now, domain and range is still all real numbers. Any linear equation, unless it's vertical or horizontal, will always be all real numbers. Okay, so we're going to read the directions here, describe the dilation in each function as it relates to the graph of the parent function. So the parent function would just be y equals x, and this got multiplied by 5. So the answer they're looking for is a vertical stretch by 5. Okay, just going to move that over a little bit. So as we look at this one here, number 11, it's going to be a vertical compression because we're multiplying all the x values by 1/3, which is going to kind of smush the graph. So vertical compression by 1/3. So as we look at our graph here, instead of going up 1 unit, right 1 unit, we're going to go up 1 unit, right 1, 2, 3 units. So 1, right 3. Now if I go up 1, right 3 again, I'm going to be off the graph. So I'm going to start at 0, 0, and I'm going to go down 1 unit, right 1, 2, 3 units. Now technically I went up 2, right 6, because our graph goes by 2s. But if I reduce that fraction, it becomes 1/3, and then we're matching that 1/3 right there. And then I just draw the line. Okay, don't forget the arrows on the end. Again, domain and range are all real numbers. So next, these are all, the top 10, 11, and 12 are all either vertical stretches or compressions. When we have the graph within, not the graph, but the number inside of the parentheses, we always take the reciprocal of this number. So just reminding you how reciprocals work, I'm going to take the number inside of the parenthesis 3, I'm going to put it over 1. When we do the reciprocal of the number, I just flip that fraction. So the reciprocal of this number is 1/3. Right? So this graph right here, number 13, is going to be a horizontal compression by 1/3 units. Okay. So when I look at this graph, 1 second here. So when I'm looking at the graph, it's a horizontal compression, so it's going to do the same thing. It's going to go up 1 unit, right 3 units. And then I can go from the middle, down 1 units, left 3 units. We'll explain a little more of this on Friday, because the issue with this unit is that when you're doing vertical compression and stretches or horizontal stretches and compressions, the graphs end up looking the same, and that's confusing. I think it's much easier to understand these horizontal and vertical stretches and compressions using x-squared graphs, but that's how it works. So we're going to move on now. Okay, when I have a negative in front of the function, it's going to reflect over the x-axis. So if I take this point and I reflect it over this x-axis right here, I'm 1, 2, 3, 4 points above the x-axis. So when I reflect it, it's going to be 1, 2, 3, 4 points below the x-axis. Okay. I think these graphs, when we're talking about the reflections, are easier if we make an XY table. So that's what we're going to do. So when we make our XY table, I leave a lot of space in the middle so you can show some work in the middle. And I always like having x comma y outside because it makes it easier to graph. And then I put the function in the middle, negative 4x, like that. So I think the easiest points to start with, especially if we don't have a fraction, are -1, 0, and +1. And we're going to go ahead and plug those in for the x right here. So we have -4 times -1. Our answer is going to be this y value right here. So we take -4 times 0, and then we take -4 times 1. So making our ordered pairs here, the x values are -1, 0, and +1. So if we multiply right here, -4 times -1, we get +4. If we multiply -4 times 0, we get 0. Right? If we reflect, the middle of the graph is 0, 0 is not going to change. If we multiply -4 times +1, we get -4. So I like picking -1, 0, and +1 because it keeps us around the middle of this graph, and it's going to be, we're more likely to find order pairs that are on that graph. So we're going to graph -1 right here. Remember, it's in the middle. This graph is going by 2's. So -1, +4 is going to be right there. And then we have 0, 0. And then we have 1, -4. So you notice the graph reflected over the x-axis and got steeper at the same time. If you try to figure that out on your own without ordered pairs, I think it gets very confusing. So I recommend doing the ordered pairs because it'll make a heck of a lot more sense. And your graph should look about like that. Not sure why it split my graph there, but it's okay. Again, domain and range here are still all real numbers. So I want to just look at number 18, and we're going to make an XY table for 18, and that'll be the last example we cover today. So I'm looking at number 18 here, and we've got a translation where it's going to reflect over the x-axis. Then we have a horizontal stretch by 3/2. It's a horizontal stretch because it's a vertical compression because the fraction is in front of the parenthesis and it's less than 1. So that's why it's going to be a vertical compression. So we're going to make our XY table here. And I'm not this time going to plug in -1, 0, and +1. The reason I'm not plugging in those values is because of the denominator here of 3. So I'm going to choose x values that are a multiple of 3. It'll make it easier when we multiply, and you'll see that in a minute. So we have x comma y. I always like doing the ordered pair there. We write the function in the middle. So multiples of 3. How do you get multiples of 3? Well, 1 times 3 is 3. That's a multiple of 3. 2 times 3 is 6. So multiples of 3, if you'll notice here, just increase by 3 each time. Remember, when I graph this, I want to get values around the origin, 0, 0. So what I'm going to choose is -3, 0, and +3. I'm going to plug all those values in right here for this x. So I have -2/3 times -3. I'm going to make it a fraction, right? Because when we multiply fractions, we always multiply straight across, top and bottom. Then I'm going to take -2/3, multiply it by 0. So when I multiply anything by 0, it stays 0. That's why I didn't make a fraction there. Then we're going to multiply -2/3 times +3/1. And again, when I multiply fractions, I multiply straight across top and bottom. So as you look at the top one here, -2 times -3 is +6. So our x value of their ordered pair is -3. The y value is, right, I get +6 here divided by 3. So I'm going to write that answer here. 6 divided by 3, and when you see it, 6 divided by 3 is 2. Ordered pair in the middle here is going to be 0, 0, because when I multiply anything by 0, I get 0. Last, I'm going to multiply -2 times 3, and I get -6. When I look down here, 3 times 1 is +3. -6 divided by 3 is -2. So my ordered pair is 3, -2. So again, especially with fractions, it gets very confusing about what's happening in the graph. I would definitely use this XY table here to help you graph these ordered pairs. So we're going to go ahead and graph the ordered pairs above. So we have -3. Remember, we're going by 2's, and then up 2. So we're going to be in the middle of that square. Then we have 0, 0, and we have +3, -2, which is going to be right here. Then you can go ahead and draw your line Don't forget the arrows on the end. There you have it. We've done all of the different examples. We have to add, I think, up here, the horizontal stretches and compressions. Okay, so we're going to do that now. So when y equals, again, it's inside of the parenthesis, 1 over some number times x. We always look at the reciprocal. So let's say our fraction here was 1/2. And when we do the reciprocal, we flip that fraction. So it's going to be 2 over 1. So it's going to be a horizontal stretch because when we flip that fraction, it's going to become a whole number. Because it's a whole number, that's what makes it a stretch. And it's going to be a stretch by whatever that number is over 1. If we have y equals a whole number within the parentheses times x, again, we're looking over here. If we use that similar example and it's 2 over 1, 2 being a whole number, and we flip that fraction, it's going to be 1/2. So that makes it a horizontal compression. By 1 over whatever that number is. All right, that is it.